Welcome to the video on alkenes and alkynes. We're going to continue our discussion of hydrocarbons. And these are hydrocarbons with double or triple bonds. Definition of an alkene is a hydrocarbon that contains one or more carbon-carbon double bonds. Simplest alkene is called ethylene. And ethylene, the simplest one, would be with two carbons, and we'll take a look at that in a minute. Alkynes, hydrocarbon that contains one or more carbon-carbon triple bonds. And acetylene is the simplest alkyne, and that's the one with two carbon atoms and a triple bond between them. Here are pictures of them. Ball and stick, and just a drawing with the symbols for each one. If you have a hydrocarbon with at least one double or triple bond, or you can say that with one multiple bond, is called an unsaturated hydrocarbon. So it has at least one bond that's more than a single bond. It's called unsaturated. If we look at the three hydrocarbons with two carbon atoms in them, ethane, ethylene, and acetylene, ethane is saturated because it's all, well, there's only one carbon-carbon bond and it's a single bond. So no multiple bonds, it's saturated. An alkene is unsaturated because it has at least one multiple bond. The same is true for acetylene. It is unsaturated. And that term, saturated, unsaturated, that refers to the number of hydrogen atoms in the molecule. You'll notice that the number of hydrogen atoms is disappearing as we go from ethane to ethylene to acetylene. And so that's where the term comes from, that an unsaturated hydrocarbon could have more hydrogen atoms in it based on the number of carbon atoms in it. Go ahead and look at these alkenes. They're alkenes because they all have at least one double bond. These all have exactly one double bond. Go ahead and write the molecular formula for each, and then come up with the general formula for an alkene with one double bond in the same kind of notation that we did for alkanes. All right, I hope you were able to go ahead and count all these things. If we look at the first one, I see that there are 4 carbon atoms, and if I count all those things, I come up with 8 hydrogen atoms. The next one has 1 more carbon and 2 more hydrogens, and yet another carbon and 2 more hydrogen atoms. In your formula for that, notice the number of hydrogen atoms is always double the number of carbon atoms. And that's the way we write it, CnH2n. And if we compare that to the general formula for an alkane, we can see that the alkene contains 2 fewer H atoms for the same number of carbons. Let's go ahead and try to draw a Lewis structure for the simplest alkene, ethylene. And then once you have the Lewis structure, use VSEPR to determine the molecular geometry for each of the 2 carbon atoms. And when we say determine the molecular geometry, that means give the molecular geometry name and the approximate bond angles. Go ahead and try that and come back when you're done. All right, I will walk you through a little review of Lewis structures. I'm going to start from the beginning for this one. We just remember the starting point for Lewis structures. You count the number of valence electrons from the formula. We look at the periodic table and see that carbon is in group 4A. That means it has 4 valence electrons. So I get a total of 8 valence electrons from the 2 carbon atoms, 1 each from each of the 4 hydrogen atoms for a total of 12 valence electrons. Draw single bonds between everything that's connected. Each of those bonds represents 2 electrons. And if I'm following the procedure for Lewis structure, my next step would be to take any extra electrons. See, I have 2, 4, 6, 8, 10 electrons in my picture so far. If I go through and count each double bond, or each single bond here, as 2 electrons, that's a total 2, 4, 6, 8, 10. I have 2 left. Normally I would put any extra electrons as lone pairs on the outer atoms, but I never put any lone pairs on hydrogen. So I would put lone pair on one of the carbons. 2, 4, 6, 8 electrons around that carbon now, but I'm out of electrons. I've used all 12 electrons, and the carbon on the right is not happy. So I would share that pair of electrons on the carbon, from the carbon, to make the carbon on the right happy. That is, to make it satisfy the octet rule, by moving the lone pair and sharing it as a double bond. And now I have everything satisfying the octet rule. Remember, hydrogen atoms are going to be connected to something, have 2 electrons near it. Everything else from the second row at least will always have 8 electrons near it, and this does. Okay, now we're going to use VSEPR to figure out the geometry of this. Count the electron regions. You look at our Lewis structure, and one thing you should note here, that for this alkene, the Lewis structure and the structural formula are the same because there are no lone pairs. That's a good thing to note when you're looking at a Lewis structure for an alkene that is just a hydrocarbon, just a simple alkene. The structural formula is the Lewis structure. So we can use the structural formula to figure out the geometry. So count electron regions around one of the carbon atoms. I'm going to choose the carbon on the left, and I count 3 electron regions. Remember that multiple bonds, this is previous material from your previous course. Multiple bonds count as one region when we're looking at determining the shape using the valence shell electron pair repulsion theory. We've got 3 electron regions, which means it's a trigonal planar electron geometry. Since there are no lone pairs, the electron geometry and the molecular geometry are the same, and we would say that our angles are all 120 degrees. Remember how you define an angle in a molecule. You define the angle by the position of atoms. So when we're talking about angles, we're talking about looking at angles where your central atom, the carbon on the left in this case, hydrogen, carbon, hydrogen angle should be about 120. And all the angles, this angle too, carbon, carbon, hydrogen should be close to 120. And this third angle, close to 120. We could do that for the carbon on the right too and come up with exactly the same thing. Here's another way of looking at them, just showing you the way we would draw the structural formula, the one in the middle. This is when you have models, you should go ahead and build the models. And you can see that these pictures are a good representation because everything is in the same plane. You have 2 trigonal planar carbon atoms connected to each other. So for ethylene, all the atoms are in the same plane, which means we can draw a simple picture. The one in the middle shows us with all the atoms of the molecule in the plane of the screen. And here, if you want to get a feel for the 3-dimensionality of the thing, if you can imagine pulling the bottom part of the molecule up and toward you, you would end up with something that looks like that. Just kind of giving you an idea that this thing is an object that you're representing with these pictures, with these drawings. Now that we've said that hydrocarbons, the structural formula, which you're looking at here, either the complete structural formula or the line angle structural formula, is actually a Lewis structure because there are no lone pairs in these things. And because of that, we can determine the molecular geometry and the angles just by looking at the structural formula. So I want you to go ahead and try to do this and go back and remember VSEPR. You have carbons with single bonds, carbons with double bonds. Apply the VSEPR to figure out the bond angles for each of the marked carbons 1 through 3 and come back when you're finished. Well, let's look at each of these carbons, and those both of these pictures represent the same molecule, by the way. And getting used to looking at the line angle formula is a goal of going through all this stuff, but start out maybe when we're looking at trying to figure out geometries by looking at these formulas. Let's look at the full one first, the one on the left. And for carbon 1, we have 1, 2, 3 regions with electrons. That's if there's a double bond to one of the carbons, that means we're going to have a trigonal planar geometry, and those angles are 120 degrees. If we look at carbon 2, when we count, I'm just going to do a little checks because it'll get too messy if I try to write numbers. 1, 2, 3, 4 electron regions. Well, that's tetrahedral, and that angle is 109 or 109.5. Carbon 3 is also all single bonds, 4 connections, tetrahedral with angles of 109.5 degrees. So we can get a lot of information out of a structural formula for a hydrocarbon. So far we've talked about alkanes and alkynes. Now go ahead and do the same thing again by just looking at the line angle formula. And here you have to remember that the hydrogen atoms aren't shown, but you can easily figure out how many there are. That this place represents a carbon with a double bond. So we see 2 connections there, plus a third connection, the single bond to the other carbon, which means there's 1 hydrogen that's not shown. So that carbon 1, it's going to be the same thing that we saw on the left because it's the same molecule. Carbon 1 is 120 degrees. Carbon 2, I see 3 single bonds. That means that there's 1 hydrogen not being drawn here. So the 4th connection that we don't see, we use that to figure out the angles. Because I have 4 regions, it's tetrahedral, which means the angle is 109.5. In carbon 3, I only see 1 connection, and that means that there are 3 hydrogen atoms that are not shown, but we know are there. And we can look at that and determine that that's also tetrahedral with 109.5 degree angles. Let's look at the naming system for alkenes. We already are pretty comfortable with alkanes by now. We're just going to add a little bit to our knowledge to be able to name alkenes. And there are a couple different systems. We want you to use the one that we are talking about in our course, the one that's contained in your textbook, the one that or how we're talking about it here. Do not look up names on the internet and answer questions using other naming systems on labs. We want you to use this naming system. Learn one, and then we can learn others later. So here are the systematic names for these. We've been talking about ethylene. That's not the systematic name. Ethene is the systematic name. We've been talking about that. And then if we look at this, this is 1-butene. And this one is trans-4-methyl 2-pentene. And this one is cis-4-methyl two pentenes. So notice that we also have cis-trans isomers for these alkenes like we did for cycloalkenes, but it's a different kind of cis-trans. And we'll have to go into that a little later. So try to come up with a naming system and don't worry so much about the cis-trans. Just be aware that it could be there. We'll talk about where it would come from, but come up with a naming system that, from these few examples as much as you can. And we'll come back. When you come back, we'll talk about it. All right, welcome back. We're going to move forward to the next slide and talk about the naming system for alkenes. Let's go ahead and go through the naming system for alkenes. You can see that they all end in E and E. That's one thing to note. That's a difference between naming an alkene. That's how it's different from an alkane. Alkanes end in A and E. Alkenes end in E and E. The root name is the same root name that we used before. Now the subtle difference that we don't really see illustrated here is that the longest chain that we're looking for must contain both carbons of the double bond. And we'll see an example of that coming up, where you have to make sure that when you're finding the longest chain that both carbons involved in the double bond are in that chain. The position of the double bonds indicated using a number, and we're going to choose the lower number, 1-butene. We look at 1-butene. That means when you see a 1, that means that the carbon of the double bond is going to be on the end. And we choose the numbering that gets us to the double bond faster. It's 1, if we count 1, 2, 3, 4. That gets us to the double bond faster than if we started at the other end and counted 1, 2, 3. So it's 1-butene, not 3-butene. We choose the lower number. It's always going to be 1-butene. Choose the red. And the cis or trans will address that later, how we can really determine. But you can see that the cis and trans have the same connections, but they are different somehow. A double bond does limit your rotation. You can't rotate it, so these are fixed. So the cis-trans comes into play when you have some constraint that prevents rotation, and a double bond prevents rotation. And substituents are named in exactly the same way they were before. We're going to find 1, 2. It's a 2-butene. Remember, we're using that number in front of the last number there. Refers to the position of where the double bond is. So 1, 2, 3, 4, and that's our 5th carbon of pentene. But the 4 position is where I have the methyl group, and that's why it's 4-methyl-2-pentene, and both of these are the same. And it's just cis and trans explain the difference between these two molecules. Let's look at these, and they're numbered in the way that we should. Hexene, 1-hexene, the double bonds at the end. 4-methyl-1-hexene. And here's where we see the first difference between just finding the longest chain and finding the longest chain that contains both atoms of the carbon-carbon double bond. If we look at the one on the right, the 2,3-diethyl-1-pentene, we're not going to use that numbering system where we have 1, 2, 3, 4, 5, 6. That is the longest chain, but that longest chain of 6 carbons does not contain both atoms of the carbon-carbon double bond. It only contains one of them. The longest chain that contains both carbons of the carbon-carbon double bond is the 5-membered chain shown with the pink numbers. And just getting used to making the connection between the line angle formula and this condensed structural formula. The line angle, getting used to looking at those is really helpful. The condensed structural formulas get awfully cluttered, even with relatively small molecules like this one. So circling those two ethyl groups, just trying to get you to see the connection between the pictures in that ethyl group down there. Getting used to the line angles as soon as you can is going to be helping you all the way through the rest of this course and any future course you take that involves organic chemistry. Let's look at this cis or trans now a little more closely. We look at these are both two butenes. We have a double bond in a hydrocarbon with 4 carbons in the chain that contains both carbons of the double bond. That means it's a butene, and they are both two butenes because the double bond starts at a carbon 1 away from the end. So these are two butenes. And now why is one cis and one trans? Well, cis means together, and we're going to talk about relative to the double bond. Is it the same side of the double bond? If it is, we call it cis together, and if they're on opposite sides, we call it trans, which is across from. So if I draw a line through the carbons with the double bond, and remember that this is a trigonal planar geometries around both those carbons, that means all 6 the carbon atoms are all in the same plane, and the hydrogen atoms connected to the carbon atoms of the double bond are all in the same plane. And so we see that those in the molecule on the left, the two methyl groups are on the same side of that double bond. It's a cis 2 butene. So the carbons of the parent chain are on the same side. If they're on the opposite side, I have to cross that line to circle my chain. Then that is trans 2 butene. And we can have substituents instead of part of the chain and come up with the same kind of naming system. But we'll see that a little later. One thing to keep in mind while you're looking at all of this is that if they are isomers, and these cis-trans isomers are isomers of each other, because they are isomers, they are different molecules with different properties. If we look at the melting points, compare the melting point of cis 2 butene to trans 2 butene, we see that trans 2 butene's melting point is much higher than that of the cis 2 butene. Their boiling points are pretty similar, but the melting points are significantly different, with it taking much more energy to melt the trans 2 butene. Those are negative numbers, negative 139 degrees Celsius for the cis and negative 106 degrees Celsius for the trans. It takes more energy to melt the trans 2 butene. It's pretty much how they fit together in a solid. That's the key point here, though. Remember that isomers are different molecules with different properties. They differ from conformations. Conformations is when you have rotations around single bonds. You can't rotate around double bonds. When do you use the cis or trans? Let's look at these. The first two do not have cis trans isomers. I want you to look at this and try to figure out why. And give it a shot and come back when you're finished. Well, welcome back. If you look at the two on the left, the two molecules, and let's look at the first one, the 2-methyl-2-pentene. Why isn't there cis-trans isomers? In order to have cis-trans isomers, you look at the carbons of the double bond again. Okay, That would be carbons 2 and 3 here. Look at each of those. For there to be cis-trans isomers, you have to see two different groups attached to each of those carbon atoms. So we just focus in looking at the molecule and see what is connected to this one. Well, I've got a methyl group up top and a methyl group down below. If I'm just trying to look at the molecule and see what's connected to that carbon, I've got the same thing connected to that carbon, methyl groups. So there's no difference in where they could be. They're both the same thing. I could swap them and I'm not changing anything. And that means that there are no cis-trans isomers. Both of them have to have different things connected. Carbon 3 there does have two different things. And when I say different things, that means that what else besides the carbon of the double bond that it's connected to, the other two things have to be different. Here I have a hydrogen, and then down here I have an ethyl group. That satisfies it, but the one on the left, I've got two methyl groups, so I can't have cis-trans isomers. There's only one molecule with that connectivity, and that is 2-methyl 2-pentene. We do the same analysis of 3-ethyl 4-methyl 3-hexene. We could start numbering from there and have the same molecule, right? Well, focus in on that carbon 3. If we look at that, carbon 3 has an ethyl group up top, ethyl group down below. Same thing. I could swap those two positions and I'm not changing anything, right? There are no cis-trans isomers for this. Again, the carbon on the left, carbon 4 here, has a methyl group and an ethyl group. It satisfies it, but I need both carbons to have two different things. So no cis-trans isomers for that one either. If we look at the 3-methyl 3-hexene, look at that carbon. We've got a methyl and an ethyl. Okay, things are looking good here as far as potential for having cis-trans isomers. We look here, we got a hydrogen and an ethyl. Two different things on carbon 4. Therefore, it is possible to have cis-trans isomers. And we're showing the trans isomer here because the chain, the longer, the bigger parts connected to the double bond carbons go across the double bond, goes across. And then this is the cis isomer because we're on the same side of the double bond with the bigger groups. The chain goes that way. So that's why there are cis-trans for the 3-methyl 3-hexene and not for the other two. Let's do another thinker buddy here where we want you to try to name these molecules. And we're practicing looking at the condensed structural formulas. These are harder to see in a lot of ways than the line angles. It might be a good idea to go ahead and draw the line angles before you try answering this too. And your choices, you want to know if they are the same molecule, constitutional isomers, or cis-trans isomers. Go ahead and give that a try and come back when you're finished. And welcome back. And if we go ahead and try to draw these as line angle formulas, I see that I have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Carbon-carbon double bond at the end. And then this one I have 1, 2, 3, 4 carbons. 1, 2, 3, 4, and the carbon-carbon double bond in the middle. So they have different connections. Okay. Name that as 1-butene, 2-butene. And because it's a condensed structural formula, we don't know if that's cis-trans 2-butene. We just know it's a 2-butene. But What we're looking at here is the difference between these two, and because the double bond's in a different position, these things are constitutional isomers. We have different connectivity. Let's do the same thing for the pair below, and we look, drawing it again, we've got 4 carbon atoms. 1, 2, 3, 4. That's 1 butene again. And then we look 1, 2, 3, 4. We look at that. That's 1 butene, just drawn differently. So that's the same molecule. Okay. Remember, we're representing molecules which are objects, and how we draw them depends on our perspective or how we choose to orient the molecule. Both are perfectly fine. There's no rule that says we have to draw the double bond on the left. We could draw it on the right. It's the same molecule. And just remember that the 2-butene in the first example, when it's a condensed structural formula like that, we're not showing the geometric information, so we have no way of knowing which 2-butene it is that we're talking about. Right now we were just interested in the difference between it and 1-butene, so that's a constitutional isomer relationship. And here's what they would look like if we did have some more structural information, the difference between cis-2-butene and trans-2-butene. We haven't talked about how to name cycloalkenes yet, but go ahead and give it a try, and we've given you a little hint on the numbering involved. So go ahead and try it, and then come back. I'll go through the naming. Well, welcome back. We see how the numbering goes. We're going to name the first one 3-methyl-cyclopentane. And even though there's only one substituent, because we have a double bond, we really have 2 things going on. Remember, for cycloalkanes, and there was only one substituent, we didn't use any numbers. But here we need the numbers to tell you where the substituent is relative to the position of the double bond. The double bond is always going to be carbon 1 of your double bond. And then we count in a way that gets us to the substituent faster. So this is the way we're going to count 1, 2. Always going to count 1, 2 as where the double bond is in your cycloalkene. And then, so you have a choice. You have 2 choices of 1, 2 that way, or 1, 2 going that way. And let me just go ahead and count the rest of the way. 3, 4, 5. And we choose the way that gets us to the substituent with the lower number. So that's why we choose the pink one. If we counted going the other way, with this being carbon 1, this carbon 2, we don't get to the substituent until carbon 5. So that's why it's not this one. And we only use a number for the substituents. We know that it's position 3 relative to where the double bond is. And so we don't use a 1 when we talk about where the double bond is for cycloalkenes. Same argument is true for 2 substituents. If we look at the alternate way of numbering this, there are only 2 ways to number when you have a cycloalkene. You have to start with 1 at one of the carbon atoms of the double bond and then go around. 3, 4, 5, 6. That would be the alternate way of numbering it. And this one, we're showing you the correct way with the pink, is 4-ethyl 1-methyl cyclohexene. And we choose that pink numbering because the 1 of that numbering gets us to a substituent with the number 1. If we do the other numbering, we don't get to a substituent until we have the number 2. So you're always looking for the first difference. We get to number 1 using this carbon of the double bond as number 1. Again, the position of the double bond is not numbered, just the substituents, and the substituents are always numbered in cycloalkenes. That's the difference between them and cycloalkenes. Here's the rule. It's all written out for you, much more detailed than I went over in the last slide. You go ahead and you count the atoms of the ring that contains the double bond. Number them 1 and 2 in the direction that gives the lower number to the substituent encountered first. Don't number the position of the double bond, it's not necessary. And then we number and list the substituents in alphabetical order like we did last time for alkanes and cycloalkenes. Well, let's look at this and use your Vesper. Remember that these formulas, because we have no lone pairs in any of these hydrocarbons, these structural formulas, even if they're line angle or kind of a hybrid kind of structural formula here, we can use that to figure out the angles. Go ahead and try to do that using your Vesper knowledge. So let's go ahead and analyze this. We have a carbon 1 here is this, and that represents a carbon of a double bond. When we know that that is a trigonal planar geometry, we know that there is another hydrogen here, but really we should be getting used to the fact that we see a double bond, that's going to be trigonal planar. If there's only one double bond, there are some unusual molecules that you'll encounter later if you study a lot more chemistry, but at this stage you see a double bond, it's going to be trigonal planar. And that's 120 degrees. Carbon 2 is over here, and that's all single bonds. All single bonds, and we're going for ideal Vesper angles here. And if you remember the cycloalkenes, there's puckering involved. All those carbon atoms aren't in the same plane, and we could get really close to the ideal angle, and so that's what we're after here. You can do the same thing in cycloalkenes too. There is a little more structural limitations due to the double bonds, but still, that we're going to use the ideal angles. There's a hydrogen that's not shown, but really single bonds, you should associate that with a tetrahedral ideal geometry, so 109.5 degrees. Same thing is true for carbon 3, right? It's just a regular old single bonds. 3 single bonds to hydrogen, a single bond to another carbon, 4 connections, 4 electron regions, tetrahedral electron geometry, no lone pairs, tetrahedral molecular geometry. Angles of 109.5 degrees. So polyenes are alkenes with 2 or more double bonds. And the naming system there is that we use penta for the longest chain that contains both double bonds now, and then diene, and the numbers correspond to where the double bonds are. So instead of just pentene, we go pentadiene. So there's an in there and then the Greek prefix. So this is the difference between just a pentene with 1 double bond and then 2 double bonds becomes pentadiene. And the 1 and the 4, 1, 2, 3, 4. We count from either end, we get the same thing there. And then here it's 2-methyl-1,3-butadiene. And we also give you the common name there, isoprene. But counting here, because we have a substituent, we are limited to which side we start counting on. If we count from the left, we get 1, 2. We run into the substituent first, counting from this side, as opposed to counting from the other side. So counting either way, we have a double bond with carbon 1, so that's a tie. But we break the tie if we start counting from the left because we run into the substituent faster if we start counting from the left, and that's why it's 2-methyl-1,3-butadiene and not 3-methyl-1,3-butadiene. Move on to alkynes. Still, we're just talking about naming and the general features of them. Acetylene is the common name. It's used so often you should know it when we're talking about the 2-carbon triple bond compound. That's acetylene. Ethyne is the systematic name. It's nice to know the systematic name too, but acetylene is used much more often. Go ahead and use your Vesper and remember that that structural formula, that ball and stick picture, is really a structural formula. It contains all the information you need. Welcome back. Let's look at that, and it should be linear, right? We've got 2 regions. 1, remember, multiple bonds count as a region when you're using Vesper. 2, and because it's a hydrocarbon, a simple hydrocarbon, there are no lone pairs. 2 regions of electrons only. There's nothing else to count. It's a linear molecule. So each carbon, this is carbon 1. Think about this is a carbon and this is another carbon of that triple bond. Do the same thing for counting 2 regions. So each carbon is linear. Remember, we're not talking about the overall shape, which also forms a line. But when we're talking about molecular geometries, we're only thinking about around each central atom in your molecule. And it's linear geometry about both of those. Each of those has a linear geometry. In more detail about that and showing you the actual structural formula with symbols instead of the balls and sticks, the 2 bonds line the bonds between the atoms are on opposite sides of the carbons. They're getting as far away from each other as possible. The whole Vesper theory in action here. And naming, we're going to follow the same rules for alkenes, but we're going to use the ending YNE to show that it's a triple bond instead of a double bond. And getting used to the line angles. These look weird when you first see them, right? You see this carbon, this is a carbon here, and a carbon here. And so when you have a straight line like that, you're trying to show, and the same one over here, that's a carbon. That's a carbon. We want to show that linear geometry in our picture when we can, and it's easy to do. But it kind of looks funny the first time you see it. Do the same kind of naming that we did before. You count from the side that gets you to the carbon of the triple bond sooner, and then name your substituents as you normally would. Let's go ahead and look at a structural formula and determine the ideal bond angles. Give that a try and come back when you're finished. Welcome back. Let's go ahead and apply the same things that we did before. Let's look at carbon 1. Maybe draw it in for yourself, a dot there to say, okay, that's the carbon there. And I'm interested in it, so I'm going to count regions around it. There's nothing that's not shown. I've got three bonds to this other carbon here, and the 4th bond to this carbon. So that means everything's shown. There are no hidden hydrogen atoms around carbon 1. So I've got 2 regions where there are electrons. That's linear, and the angle for linear is 180 degrees. Let's look at carbon 2. Carbon 2 in this thing has nothing to do with multiple bonds. It's a single bonded carbon. There's a hydrogen atom not shown, but I just see that it's single bonds. I can say 109.5 right away. Same thing is true for carbon 3. No multiple bonds. All of these hydrocarbons, none of them have lone pairs. The structural formulas are my Lewis structures. So again, 109.5 degrees. Now it's my job to name it. I have to find the longest chain that contains both atoms of the triple bond. And if I start counting from either side, I end up with running into the triple bond at the 3rd carbon. So just count from this side and just show 2, 3, that would be a 3 hexine, 4, 5, 6. I can go either up or down, it doesn't matter. If I go down, then this is a substituent. If I go up, then this one would be the substituent. So this is another substituent. So counting either side, I'd get the same picture, same numbering, and it would be a 2, 5 was where these substituents are in their methyl groups. So 2,5-dimethyl 3-hexyne. Common names, you do encounter them so often, especially ethene. Ethylene is used really often, and propylene is used really often. Isobutylene, something you won't see as much, but it's still a very common name. You might encounter these. You should probably be aware of them, yes. If we look at the alkynes, acetylene is used far more often than ethine. Methylacetylene and dimethylacetylene are also used quite a bit. And those are really, really common.